Hello everyone and welcome to the next lecture in machine learning for core engineering disciplines. In the last several videos you have seen how various types of loss functions are defined for ML models, and the obvious question to ask next is how would we minimize the loss function to obtain the optimal values of the parameters. So in a few cases so far we were able to do this analytically, and that was for the example of linear regression or ridge regression. But there are many cases when it's not possible to find the optimal set of parameters analytically. For example, using lasso or using logistic regression, softmax regression, or any of the more complex models like support vector machines, neural networks, Gaussian process regression, gradient boosted decision trees, and so on and so forth. So in today's lecture we will take a deep dive into how we can numerically tune parameters for machine learning models. So let's go ahead and get started. The topic for today is training of ML models. And typically ML model parameters are optimized numerically using an optimization algorithm. Okay, and the most commonly used optimizer in ML is a type of a gradient descent also called steepest descent algorithm, right. So there are various types of gradient descent algorithms, right. Particularly some of them are called stochastic gradient descent, and those are the ones which are most widely used in machine learning, right. Now let's see how this gradient descent algorithm or the steepest descent algorithm works. So how does this gradient descent algorithm work? To explain it, let's consider beta as the vector of parameters and let L denote the loss function. So what we want to do is we want to update the value of beta. We want to update beta so that we move in the direction of the decreasing loss function. So how do we move in the direction of the decreasing loss function? We have to find out what that direction is. So to do that we write a Taylor series around the point beta for the loss function. So this Taylor series will look as follows. So L at beta plus delta beta, right. The delta beta is the change in the vector of parameters that we are making is the value of the loss function at beta plus a first order term involving the gradient of the loss function and the vector of parameters, the change in the vector of parameters, and a second order term involving the Hessian of the loss function. Okay, and higher order terms. Okay, so this is the gradient, and this H is the Hessian of the loss function. This is similar to a Taylor series that you can write in one variable, right. So, if there were just one variable, right, if L was just a function of x, you would say L is L at x is L at the reference point x naught plus f dash x naught times x minus x naught plus 1 over 2 factorial f double dash x naught x minus x naught whole squared plus the higher order terms, right. So, this is what you do in case of just one variable, Taylor series in one variable. This is a Taylor series in p variables, right, because there are p parameters that we want to determine, right. So, this is the Taylor series we have written, and what we have done is we have generalized the scalar form, right, of the Taylor series to a vectorized form wherein the gradient of the loss function and the Hessian of the loss function appears, right. We will see in a moment, right, how the gradient and the Hessian look like, but assuming at the moment that we know how to compute the gradient and the Hessian, let us see, right, what happens if we just consider this Taylor series to first order and examine what we can do to make sure the loss function goes in the right direction, that is the direction of the decreasing loss. So, considering up to the first order, we can write L of beta plus delta beta is equal to the loss function at beta plus the gradient L transpose times delta beta, right. Now, as I said, what we desire is that your L of beta plus delta beta should be less than or equal to L of beta, right. Obviously, only then the loss function will reduce. If you recall, we are trying to minimize the loss function so that we get the optimal set of parameters. So, it is extremely important to ensure that the new value of the loss function when you have updated the parameters is less than or equal to the previous value of the loss function. So, how do we ensure this? So, this can only happen if the second term here on the right hand side is less than or equal to 0. So, this can happen only when your delta L transpose times delta beta is less than or equal to 0, right. So, this can be ensured with the highest magnitude right. Remember, we not only want the loss function to reduce, but we want it to reduce in the largest possible quantity. So, this can be ensured with the highest magnitude if your delta beta vector points in the direction of the minus of the gradient of L, right, because then whatever term we had written here, right, delta L transpose delta beta, that would be equal to delta L transpose times minus gradient of L, and this would be minus the gradient of L norm squared, right, which is certainly a quantity that is less than or equal to 0 and of the highest possible magnitude, right. So this is what is meant by steepest descent, right. So we have taken a descent, right, in terms of the value of the loss function in the steepest possible manner, or in other words we have moved in the direction of the negative gradient. So we have descended in the negative gradient direction. So that is why the name of this algorithm is gradient descent or steepest descent. So therefore in gradient descent or steepest descent, we update the parameter vector as your beta at iteration k plus 1 is equal to beta at the iteration k minus the gradient of L at beta k, right. So this is the direction in which you want to move the parameter, and we add a scaling factor in front of it. This scaling factor is very important. This is called the learning rate. This gamma is called the learning rate and is crucial, right, while training the ML model. So is crucial for the ML model training process. Okay, and the learning rate is what decides how aggressive the optimizer is. So if this gamma is very high, that means the optimizer is aggressive, we are trying to make larger and larger steps, and if gamma is small, right, we are taking lower and lower steps. So gamma, the learning rate, it decides how aggressive the optimizer is. Okay. So with this understanding, now let us see how we can get the gradient of the loss function and the Hessian of the loss function. So the gradient of the loss function looks like the following. Gradient of L, right, at the point beta k is equal to the partial derivative of the loss function versus each of the parameters. So let us say the parameters are b1, b2, b3, beta 1, beta 2, beta 3 up to beta p. So we take del L del beta 1, del L del beta 2, and so on and so forth up to del L del beta p, which is the last parameter, and this is evaluated at the kth iteration, right. So k denotes the index of the iteration, k is the index for the optimizer iteration, right. So you start at the 0th step and then keep on iterating till your value of beta is optimized. So let us see how this works out. So we have to compute this loss function at the point, right, beta 1 k, beta 2 k, all the way up to beta p k, and similarly the other partial derivatives have also to be computed at the same values of beta 1, beta 2 all the way up to beta p. So, I hope this clarifies how the gradient of the loss function is obtained. So, let us go ahead and look at what the Hessian is, right. So, although in the gradient descent algorithm we do not include the Hessian term, but the Hessian plays a very important role in deciding if we have really reached a local minimum or not in terms of how the loss function changes. So, let us examine closely the Hessian. So, like I said, the Hessian H plays a very important role in deciding whether a local minimum has been reached for the loss function L. Now, again I would like to draw a parallel to a 1D function, right. If you saw earlier, for the Taylor series we had drawn the parallel with a 1D function. So, we said that this is how the Taylor series looks when you have a function of one variable, but when you have a function of p variables, right, beta 1, beta 2 up to beta p, then that is how you write the Taylor series. So, what happens when we do this for the second order derivative test, right, that determines whether you have reached a minimum or not. So, if you had a one dimensional function, right, and again I will plot f of x as a function of x, right, and let us say you had a local minimum at some point x naught here, you know that at this local minimum your f dash of x naught, the derivative is equal to 0, right, and you know that the second order derivative f dash x naught, f double dash x naught should be less than 0, right. So, this is key for a local minimum, and instead if f double dash x naught was greater than 0, you would have a local maximum. So, what is the equivalent of this for a multidimensional function? That has everything to do with the Hessian H. Okay. So, how is the Hessian H defined and why does it play such a prominent role? Let us look at that. So, this is how the Hessian is defined. So, H, right, which depends on all the parameters beta 1, beta 2 up to beta p, is basically a matrix of second order derivatives. So, it is del square L del beta 1 evaluated when your beta 1 is equal to beta 1 k, beta 2 is equal to beta 2 k, and beta p is equal to beta p k, right. So, I am not going to write the argument after this double derivative, but you can see how this is being done. So, that is the first entry in the first row. The second entry in the first row is del square L del beta 1 del beta 2, and then you have del square L del beta 1 del beta 3 and so on and so forth up to del square L del beta 1 del beta p. So, that is the first row of the Hessian matrix. What happens in the second row? In the second row you have del square L del beta 2 del beta 1, then of course you have on the diagonal del square L del beta 2 squared, and finally at the end you will have del square L del beta 2 del beta p. Okay, and in the last row, right, so this will be a p by p matrix because there are p parameters. It will be del square L del beta p del beta 1, del square L del beta p del beta 2, and all the way up to del square L del beta p squared. So, I hope you can see how the Hessian matrix is constructed. So, the Hessian is typically a symmetric matrix if L is continuous and twice differentiable. And that is because if L is continuous and twice differentiable, these second order derivatives will be equal. Del square L del beta 2 beta 1 will be equal to del square L del beta 1 del beta 2, and similarly your del square L del beta p del beta 1 will be equal to del square L del beta 1 del beta p, and finally your del square L del beta p del beta 2 will be equal to del square L del beta 2 del beta p, right. And of course on the diagonal you have all the second order derivatives with respect to one of the functions. So I hope you can understand why this is a symmetric matrix, right. These terms are all equal, okay. So if you want to physically understand what the Hessian is, in simple words, the Hessian is the matrix of second order derivatives. So in simple words, the Hessian is the matrix of second order derivatives of the loss function, in this case with respect to the parameters. Okay. Now why is the Hessian so important, right. So this requires sort of a detailed discussion of the math that exists behind this, and I believe it is useful to go into the math, right, because that will give you a lot of physical insight into what is really happening. So let us go ahead and understand why this Hessian is so important. Now there can be three cases, right, just like here in the second order derivative test for one dimensional function, you could either have the second order derivative less than 0, equal to 0 or greater than 0, and those would correspond to a less than 0 would be a local maximum, and yeah, I think I need to fix this. This would be greater than 0 for a local minimum, and then it would be less than 0 for a local maximum, and then equal to 0 for a saddle point, right. So let us see what happens in the case of a multi-dimensional function, right. So for a Hessian there can again be three cases, right, and these depend on the eigenvalues of the Hessian matrix. So what is an eigenvalue, right. So if you have the Hessian matrix H, right, and you write this equation HV equal to lambda V, right, if this equation is satisfied for values lambda and V, then this lambda is called the eigenvalue and this V is called the eigenvector, okay. And whether you have reached a local minima or a local maximum or a saddle point, it depends on these eigenvalues, right, of the Hessian matrix. So you already know the Hessian matrix has size p by p, right. So it can have at most p distinct eigenvalues. So there are several cases, let us write those down. So if all eigenvalues are positive, then the Hessian is positive definite, right. So this is a new term that we are introducing here. The Hessian is positive definite and the point considered is a local minimum. So the loss function has reached its lowest value at this point, right, which is where you compute the Hessian. So this is the point where the Hessian is determined, right. So, that is if all the eigenvalues are positive, right, and the meaning of positive definite is that if you had a vector z, any vector z, right, then z transpose h z would be always positive. For any vector z for which this product is defined, right, and yeah, you can put these arrows here if you would like. So, that is the meaning of positive definite. The second case corresponds to when the eigenvalues are all negative, and then we have the case when the eigenvalue, some of them are positive and some of them are negative, right. So, now why does it matter, right, that the point is a local minimum if the Hessian is positive definite, or in other words z transpose h z is always positive for any vector z, right. So, let us try to understand the link between these concepts, right. So, recall the Taylor series. This stated that L at beta plus delta beta was equal to L at beta plus the transpose of the gradient of the loss function times delta beta plus half of delta beta transpose Hessian times delta beta, right. So, you look at the similarity here, right, you have Z transpose H z here and you have some delta beta transpose H delta beta here, right. So, if this is always greater than or equal to 0, right, then what will happen? So, if the gradient is 0, then your delta beta transpose H delta beta determines the sign of L beta plus delta beta minus L of beta. So, if the Hessian is positive definite, then L of beta plus delta beta minus L beta, right, will be greater than equal to 0, right. Why? Because at the minimum the gradient is 0. So, this term goes off. So, whatever is remaining, that determines the sign of L beta plus delta beta minus L of beta, right. So, if the gradient is 0, then as the Hessian is positive definite, then L of beta plus delta beta minus L of beta is greater than equal to 0, right. So, this means if you move in any direction from the considered point, if you move in any direction delta beta from the considered point, the value of L will increase. And what is a point from which if you move in any direction all the values always increase? That is a local minimum. Right. You can see this in action even in a simple 1D case, right. At the local minimum, if you move to the left or you move to the right, the value of the function always increases. So, that is why the second order test has to be positive. In the same way, if you have a multidimensional function, loss function of parameters beta, then you want it to increase in any direction if you are at a local minimum, and that is ensured by the Hessian being positive definite. Okay, so I hope this clarifies the link between a local minimum and the concept of the positive definitivity of the Hessian matrix, right. Now there is another curious thing that we stated here. I mean, for those who are new to this kind of thinking, is we said that if all the eigenvalues are positive, then the Hessian is positive definite, right. So one can ask the question as to why, if the eigenvalues are positive, the Hessian will be positive definite, right, and that is a question we will reserve for the next lecture. So right now we are at the end of this particular lecture. So today we discussed how we can numerically optimize a loss function which depends on p different parameters, beta 1, beta 2, all the way up to beta p, and we said that this is typically done through the use of a first order optimization algorithm like the gradient descent method, although some variants of it are used in practice. And at the heart of it, the steepest descent or gradient descent method says that to reduce the value of the loss function, you have to go opposite the direction of the gradient. So that is when you will descend. And then we introduce the concept of the learning rate, which decides how aggressive your optimizer is. We also talked about how we can really find out if we are at a local minimum by introducing the Hessian matrix and the concept of the positive definiteness, which said that at a local minimum, if you move in any direction, the value of the function will increase, and that is why the Hessian has to be positive definite. What we did not discuss is the link between the positivity of all the eigenvalues and the positive definite nature of the Hessian matrix. That is something we will discuss in the next class. So I hope to see you next time, where we will delve deeper into this. Thank you for joining today.